Solving absolute value inequalities algebraically. In example 1, I'm asked to find all real values of x such that the absolute value of x is less than or equal to 5. So graphically, this means I'm looking for all real numbers which have a distance of 5 or less units from the origin or from 0. So the first number I'm going to start with is the number 5, because the number 5 is exactly 5 units away from 0. And any number less than 5 will be less than 5 units away from 0. Looking at negative 5, I see that negative 5 is exactly 5 units away from 0 or from the origin. And any number greater than negative 5 will be less than 5 units away from the origin or from the 0. So my solution will be x is less than or equal to 5, and at the same time it must be greater than or equal to negative 5. In example 2, I'm asked to solve for x if the absolute of x plus 3 is less than or equal to 6. So I'm going to do this using two methods. So the easiest method, I think, is if you say x plus 3 is less than or equal to 6, and at the same time greater than or equal to negative 6. So I need to solve for x. To solve for x, I'm going to transpose 3. So I'm going to move 3 to the right-hand side, and I move 3 immediately to the left-hand side. And if I'm moving a term across, I know I changed the sign. So I write x is less than or equal to 6 minus 3, but greater than or equal to minus 6 minus 3. So my solution are all the numbers less than or equal to 3 and at the same time greater than or equal to negative 9. In the second method, I'm going to use the definition of the absolute value the definition of the absolute value, and I say that x plus 3 must be less than or equal to 6, and at the same time minus x plus 3 must be less than or equal to 6. So now I'm ready to simplify further. So I have that x must be less than or equal to 3, and if I distribute the negative sign, I have minus x minus 3 must be less than or equal to 6. So I have minus x is less than or equal to 9. I'm going to divide both sides by negative 1, and you remember when you divide an inequality by a negative value, the inequality sign changes. So x is greater than or equal to negative 9. And I can write this as x needs to be smaller than or equal to 3, but greater than or equal to negative 9. So in example 3, I have the absolute value of x must be greater than or equal to 2. So once again, I'm looking for all real numbers which are 2 or more units away from my origin or from 0. So looking at my 0, I see that 2 is 2 units away and negative 2 is 2 units away. But I want values of x which are more than 2 units away from 0. So all numbers greater than 2 will be more than 2 units away from 0, and all numbers less than negative 2 will also be more than 2 units away from 0. So I write my solution. My solution will be x must be less than or equal to 2. Sorry, negative 2. All numbers smaller than negative 2. Or all numbers greater than 2. So here we use the word or. In example 4, I'm asked to solve for x, and I have the absolute of 2x minus 9 is greater than or equal to 5. So using the method that I used in the last example, I am going to say that 2x minus 9 must be less than negative 5, or 2x minus 9 must be greater than positive 5. And now I solve for x. So I have 2x. If I take the negative 9 across, I'm adding 9. So 2x is less than 4. Dividing both sides by 2. X is less than 2. The inequality symbol does not change direction because I'm dividing by a positive number. Then I have 2x must be greater than 9 plus 5 is 14. So I have x must be greater than or equal to 7, and each time my inequality should have been greater than or equal to, and here it should have been less than or equal to. So any value, any real number less than or equal to 2, or any real number greater than or equal to 7 will satisfy this inequality.